Today we want to go back over both parts of the fundamental theorem of calculus. We know that the fundamental theorem of calculus is divided into two parts, the definite integral part and the one we learned on Friday, the construction part. That's the part that allows us to construct antiderivatives. Here's what we need to start the fundamental theorem of calculus. F of x is a continuous function on a closed interval, and c, which we'll need for the second part, is any value from the interval on which the function is continuous. The first part of the fundamental theorem of calculus is the one that we learned in chapter 5. The definite integral from a to b of f of x dx is capital F at b minus capital F at a, where capital F is an antiderivative of little f. That is, capital F prime is little f. The second part of the fundamental theorem of calculus says that if we define this function, from c, if we take the definite integral from c to x of our continuous function, little f, oops, I can't use x because I'm using x as an endpoint. If we define a function to be the definite integral from any fixed value to the value x of f of t dt, this function, the function defined this way, is an antiderivative of little f. So this is the part where we're constructing an antiderivative using the definite integral. We construct an antiderivative using the definite integral we construct an antiderivative using the definite integral, and this is useful because we can always approximate the definite integral with area. So this is useful. We can approximate the definite integral to any degree of accuracy with area. We can approximate the definite integral using area. And if we have a continuous function, we can do this to any degree of accuracy we need. And it's just length times width. And that's the great thing about this. Area is just length times width. So although we can't write down a nice function that is a finite combination of elementary functions to represent an antiderivative, or even if we cannot write a nice antiderivative, we can evaluate the antiderivative at any point. Any questions? Our classic example of a function with no nice antiderivative is little f of x is e to the minus x squared. This function does not have a nice antiderivative. But if we need to calculate, if we need to describe the antiderivative, we can construct an antiderivative with a definite integral. So first, we'll notice that e to the minus x squared is continuous for all real numbers. So we say continuous everywhere. Oh, I spelled y wrong. So I can construct an antiderivative with a definite integral. We can start this anywhere. It's convenient to start at 0, so since I'm plugging x into the definite integral in as an endpoint of my interval, I use a different variable. So I'm not plugging x into itself. If you've seen the film Being John Malkovich, you know why you don't want to plug x into itself. It just creates all kinds of problems. Since f of x is continuous anywhere, we can start our definite integral anywhere. So since f is continuous everywhere, we can start the definite integral from anywhere. It's convenient to start at 0. Now, we don't have a nice formula for capital F, the antiderivative, but I can evaluate this function anywhere. So if I make a table of values for x and f of x, when x is 0, we integrate from 0 to 0 of e to the minus t squared dt, and we get 0. Then to evaluate the function at other points, oh, this is the one I was using last time. Then to evaluate the function at other points, we just integrate the function with respect to x from 0, let's say from 0 to 0.1. And so that will give us 0.0, why don't I do 0.1? Let's just go from 0 to 1. From 0 to 1, we integrate from 0 to 1 and we get 0.747. So if we integrate to 2, we get 0.882. So we can evaluate this function anywhere we want. We don't have a nice formula for it. We have to integrate, but we can just do, all our calculator is doing to calculate these definite integrals is approximating the area. Now in this case, f of x is the antiderivative of e to the minus t squared. So in this case, we started off at 0, but we can start anywhere we want. It could be that for a particular problem, 0 doesn't really have any meaning for us, and we would want to start the integration at -1. We can start wherever we want. So I can define another function, say g of x, to be the integral. Since we can start anywhere we want, maybe we need to start off at -1 for reasons. And we can evaluate, we just set up a different table, so x and g of x. When x is 0, we'll get a different value because we're going to want to integrate the function, let's say, from -1 to 0. And now we get 0.747, like we did before. Then if I evaluate at 1, we'll integrate from -1 to 1, and we get 1.494. At 2, we get 1.628. And at 3, we get 1.633. Any questions? So even though I don't have a nice simple formula for the antiderivative of e to the minus t squared, I can still come up with values for at any point we're concerned with. Moreover, if we look at the amount of change, let's say from 0 to 0.747, here we see an increase of 0.747. The change from 0 to 1 is 0.747. We also see that same change in g of x. This has all just been shifted up by 0.747 units. So we have an increase of 0.747. If we look at the increase from 0.747 to 882, so 0.882 minus 0.747, we have an increase of 0.135. And if we look at the increase from 1628 to 1494, we also have an increase of 134. Not exactly the same as 0.135, but these values have been rounded off, so we should expect things to be different at the place we rounded things off. If we look at the change from 0.882 to 0.886, we have an increase of 0.004, and the same thing happens down here. We have an increase of 0.005. So at least now we can see where the round off happened. So the amount of change is the same. So the derivative is still the same. So g of x is just f of x shifted up 0.747 units. The shape will be the same. The graph will just be shifted up 0.747 units. Also, since we are constructing antiderivatives, since capital F is an antiderivative of e to the minus t squared, if I take the derivative of this function, capital F prime at x will just be e to the minus x, it's x again, e to the minus x squared. Similarly, capital G is an antiderivative of e to the minus t squared. So the derivative, capital G prime of x, is e to the minus x squared. Two different antiderivatives of the same function. Any questions? Another important example of a function that does not have a nice antiderivative is the sine integral. So it's a special function si of x, and it's defined to be the integral from 0 to x of sine of t over t dt. It's a function whose definition is based on the definite integral. This function is an antiderivative of sine of t over t. So the sine integral is an antiderivative of sine of t over t because we constructed it with the second fundamental theorem of calculus. And so what that means is that we take the derivative of this function we'll get sine of x over x. We don't have a nice closed formula for the antiderivative of sine of x over x, so we construct one using the second fundamental theorem. Any questions? This is an important enough integral that it has its own Wikipedia entry. It's a sub-entry of trigonometric integrals. Any questions? Comments? Snide remarks? All right, let's pause the video here and talk about other things that we need to talk about.